Okay, hello everybody. I'm going to go over instrumentation homework for you. Okay, exercise 7.1. Hopefully straightforward. Potential dividers, nice and easy. So P is 8.4K, so let's work out the voltage there. And the variable resistor is 10.3. So what I always do is I work it out as kind of two different bits. So we'll call that Vx for argument's sake, and we'll call that one Vy. Okay. So Vx equals, by ratio, it's going to be 10.3 over the total, which is 10.3 plus 8.4. What's that? That's 18. 18.7 multiplied by your 12 gives me this value here. Just looking at my answer, it'll be easier to do that. 6.61. 61 volts, and then Vy, we'll do exactly the same. Vy is going to be 10k this time over the total, which is still 18.7 multiplied by 12 gives me 6.42. Then obviously V out is the top of the arrow minus the bottom of the arrow. So V out equals Vy minus Vx. So in this particular case, Vy is lower than Vx. So the answer will be a negative value minus 0.19 volts. Okay. I think it's exactly the same for doing this. So let's do this. Okay. So VP, we'll call it, voltage at this bit here is 100 lots of the total. What's the total? The strain gauge S is 100.5. So 200.5 times your 12. So voltage at P is 5.985. You need to go to at least 3 decimal places, I would say, for this one, yeah? So don't round that. 5.985, don't just say that's 6 volts, because obviously you're not going to get to the accuracy there. Voltage at the next one, which is Q, VQ, is 100 over the total, which, where's Q? Dummy strain gauge is 100, so it's literally 100 over 200 times your 12, which is 6 volts. But I'm going to write it out like that. That's how you should write it out if you're going to the same decimal places. 6.000. And then obviously the difference is Q minus F, so V diff equals VQ minus VP. Sorry, yeah, Q minus P, sorry. So again, Q has got a lower number than P, so a higher number this time, so it should be a positive answer, 0.015 volts, okay? And part B, why do we need a dummy strain gauge? Basically keeps it calibrated. So it says in the marks, dummy strain gauge prevents V-diff changing when the strain gauge resistance changes due to some external factor. The external factor, generally speaking, will be temperature changes. So if the temperature changes or any other external factor, you want to keep it calibrated. So if obviously if the resistance there goes up, the resistance there will go up by the same amount. V-diff will remain calibrated. Have a look at the mark scheme if you want to have a look at the actual answer. Okay. Moving on to this next one. Okay, 7.2. So this time, this is a bit of a weird one. So for a thermistor, as the temperature goes up, the resistance goes down, which obviously means that the voltage will go down as well. So you need to think, it says here, draw a circuit diagram to give the output voltage. So V diff increases as the temperature increases. So temperature goes up, resistance goes down, and I want V diff to increase. So there's different ways you can do this, but I know that it's going to be, and again, if you get it wrong, you can change that. So this is a thermistor of the top. This one's a thermistor on the bottom temperature, sorry. I'll just put B for bottom. And then obviously, does it need to be variable? Let's have a look. Say anything about variable? I don't think it does say anything about variable. Oh, it does, yeah, variable resistor. So variable. So think about this. It says it needs to change if the temperature increases. That's measuring the top temperature. So if that temperature goes up, the voltage will go down. If the voltage goes down here, it's the same as me saying that the voltage is increasing at this point here. So it's going to increase V diff. Now, if you get it the wrong way round, you'll lose 1 mark. So it's not the end of the world. Okay. But obviously try and think about it. Maybe just draw it at the side. I hope that makes sense. See me if you're unsure on that one. This is dead easy. It's the equation. V out equals V diff multiplied by gain. So in this particular case, the difference in voltage is going to be V1 minus V2. Just look which one has the higher voltage going into it. The top temperature does, which is 2.4 volts. So it's going to be a positive answer. No, it's going to be a negative answer. So look at this one. It's going to be 2.4 minus your 2.1 multiplied by the gain, which is obviously 200 over 10, which is going to equal, where are we? Minus, well, going to equal 6 volts. It's going to equal 6 volts, but V1 is greater than V2. So V1 is greater than V2. So V out equals minus 6 volts. You could put it in there and put a minus sign there, but I've just done it as a positive answer, but then just check which one has the bigger number going in. Look, V1 goes into the inverting input. It's got a bigger number. The answer is going to be negative. Okay. This one, this is obvious, this as your strain gauge. So you can do them as potential dividers circularly, but I think you guys, when we did this in lesson, decided to draw them straight away like this, which is what I am going to do. Like that. This goes off to the power supply, and this goes off to your, oh, one down. These bits go off to there. I'll go off to your power supply. Don't need to worry about that. We'll just stick 12 volts and 0 volts on there. Okay, so we've got strain gauge. We have to label it. Do we want a dummy strain gauge? Is it asking us to do that? Don't think it is. It's just saying strain gauge, 2 equal resistors and a variable resistor. So strain gauge. That's your strain gauge. You've got 2 equal resistors and a variable. Doesn't matter which one you put as a variable resistor, actually, because it would still change. I'm going to put the bottom one. Doesn't have to be the bottom one. Okay, and 2 fixed resistors. There we go. What is the advantage of this arrangement over simple voltage divider and amplifier? I'm going to show you the mark scheme. Saves me writing it down, but it's hopefully straightforward. That the mark scheme here is changes in the power supply voltage affects both the inputs, so will have little effect on V out. So essentially, if you get fluctuations there at this point here, hopefully you can see my cursor. If not, I'll just draw it here. If you get fluctuations in voltage here, basically V1 and V2 will both change by the same fluctuations. Therefore, V diff will remain unchanged. Another advantage is you can actually amplify small changes in V2. So V2 connects into there, you can amplify that. If you've got a normal op amp, you can only amplify V1, can't you? Because V2 connects to 0 volts. So that's another advantage. And the third advantage is obviously good immunity to electrical noise, because again, if you get voltage spikes, both of the voltages will go up or down by the same amount. They'll be cancelled out. Hope those 3 ideas just make sense logically. Point 1 and point 3 are very similar, really. But apart from we're talking about electrical noise for point 3, and point 1 is just about random changes in the power supply voltage. Okay. And then the last one, dead easy. It's just basically, can we use the equation? V out equals V diff multiplied by the gain. I'll write it like that. Okay, so look at the question. We've been given the difference in voltage, and we've been given V out. Okay, so we obviously want to work out the ratio for that one. Okay, so rearrange the equation. So V out over V diff equals RF over R1. Okay, so in this particular case, 2.4 over the difference in voltage, which I'm just going to look up, say we use my calculator, 0.012 equals 200. So I'm going to use RF, I'm going to use, RF is 200k and R1 is 1k. Okay, and then label it. It says label your circuit diagram. So the circuit diagram above, just label that. Okay, that's exercise 7.1, 7.2. I'm going to do 7.3 for you next.